back. All right, so as I told you last time, I'm going to talk about how to construct these advanced cryptographic primitives, and they're going to use lattice trapdoors. Now, in case you were not there for the last talk, or if it didn't make sense to you or any of that, you don't really need to know how to construct trapdoors for this talk. You just need to know that there exist trapdoors, okay, and the sort of minimal thing that we need to know as a black box is that there's a way to sample a fat matrix A from ZQ n by m along with some trapdoor T, which implies the inversion of SIS and LWE using A, of course, right? So that's all that you need to know. And knowing this, the current talk should be completely clear. So it's self-contained, okay? So if there's anything that I say that doesn't make sense to you, please stop and ask me immediately. There's no context that you have to assume anymore, okay? So this is all that you need to know. All right, great. So let's talk about how to build these crypto systems. It's stuff I love, and I hope you'll think so as well. So I was telling you about identity-based encryption, and the fact that we're going to have the following broad structure. We're going to use regev encryption, but now we have this string, this ID, that needs to be embedded both in the ciphertext and in the key. And the way we're going to do it is we're just going to find a way to put it in a matrix. So this matrix A that I told you about, okay, so not this exact matrix, but I'm going to construct a matrix in which I somehow embed this identity. There's different ways of doing it, as we'll see. And then I'm just going to perform basic regev encryption using this new matrix. Okay, so is that clear? So I'm just going to call it FID. All right, so this is what I'm going to do. So let me start with the following construction, which was by Cash et al. From 2010. Let's assume that the length of the string is just 2. It's just a 2-bit string. In fact, I'm also assuming that it's binary for now. And what we're going to do is we're actually going to blow up the parameters according to the length of this identity in the following way. With every position, I'm going to associate 2 matrices, one corresponding to the fact that I equals 0 and one to the fact that I equals 1. So since we have length 2, this gives me 4 matrices. And then there's going to be like a special matrix here, A0, along with a vector U. So this A0 and U are going to be used, like if you remember in the regev encryption, there's an A transpose S plus E and a U transpose S plus E plus message. So the U is always the same, and this A0 is going to be somehow special, as we're going to see. So the master secret key is just going to be a trapdoor for A0. Okay, so that's our master secret key. And now I told you that I want to construct this, FID. Here, let's think of ID as just 01 for concreteness. So I need to construct this F01 and sample somehow a short E such that F01E is congruent to U mod Q. So how do I construct this F01? So just based on what I told you, any guesses? Just by looking at the public key. So I want to embed 01, yeah, in this matrix. And what have I given you? I've given you, let's forget A0 for a second. I've given you 4 matrices, right, with 2 per position. So how should I construct F01? I mean, what's the most natural thing you can think of given these?
0 and A21.
Sorry?
First one and the last one.
Exactly. So you choose, according to the value of the bit I, you choose the corresponding matrix. So we'll do that. But we'll also put this A0 there. So from the perspective of key generation, it should be obvious that you need something to do with A0 because that's the only thing for which you have a trapdoor. So there's nothing, I mean, there's nothing you can do without it. Fine, so I'm going to construct my matrix in this way. Notice that it's not particularly efficient because it's going to grow one block per bit. We're going to see how to improve that in subsequent slides. And I need to give you this E, right, such that this relation holds. But I only have a trapdoor for A0, so I don't have a trapdoor for the whole matrix. But it turns out to be a not very difficult exercise to figure out how to extend this trapdoor. So can you take a shot at it? So if this is my F, I have a trapdoor for A and I want a trapdoor for F. What's a trapdoor? Just short vectors, or just a matrix, a short small valued matrix, such that F times that matrix is 0 mod Q. That's a trapdoor, right? So we'll just think of these short bases for simplicity as our trapdoors for now. So given a trapdoor for A0, how should I, so I have this A0 and I have A10, A21, right? And this guy has a trapdoor. And now I want to sample a short vector E, E0, E1, E2 such that this holds. And if I get sufficiently many of these, that's a full basis, right? So how should I do this? I have a trapdoor for A0. So we saw something like this in the previous talk. Any ideas?
Choose E1, E2 small random.
Very good. That's exactly right. So it's exactly, I mean, it's exactly what Hari said. You choose E1 and E2 randomly from the right distribution, and then you get some linear relation with these matrices and these vectors, in which the only thing that's not instantiated is E0, right? But you have a trapdoor for A0. So you can sample E0 to satisfy whatever dependency you want. Okay, so now again you might need to re-randomize this, but let's not worry about that. So the point is I can get a trapdoor for this extended matrix, and once I have that trapdoor, then I can compute this vector E. And now encryption is easy, right? So encryption is what? It's just A transpose S plus E and U transpose S plus E plus noise, where I told you that we'll replace the A with this F matrix. So let's just do that, and that's all. So I mean, since this is our first example, I've worked out decryption. I mean, I've written everything down explicitly, but it's really very, very simple, right? So once you know you want to use the Regev scheme, it's exactly that, just with this one drop in. So it's exactly the same decryption equation. All right, so is the scheme clear? Okay, so that's great. But now why is it secure? So it turns out that proving security of these constructions is actually quite difficult in general. And the reason is the following. I mean, if you think about FHE, then the tough thing to get in FHE is the functionality, right? But once you somehow find a way to get the functionality going, the security that you want is just semantic security, because all the attacker ever sees is a bunch of ciphertexts. But in the case of something like IBE, the attacker does not just see ciphertexts. She also sees more, right? And that's captured in this game. So as usual, we'll model it as a game between the challenger and the adversary. So the challenger will get an instance of some hard problem, LWE for us. And we're going to consider a sort of weak version of the game, which is called selective security, in which the attacker, in the very first step, sort of gives the challenger the challenge identity. So maybe I'll just say before I show you formally. So the goal is to the goal for the attacker is to distinguish between two ciphertexts, one for M0, one for M1. This is standard, but now with respect to the same identity. And the attacker, of course, can choose her own, worst case identity ID star. In the selective game, we'll make it sort of declare this identity at the very first step. So this is not optimal, but for now we'll just stick with it. So the attacker gives this, gets the public key, and here's the crucial step, right? So in this security game, unlike in FHE, there is a notion of, there's a notion of getting keys for the attacker. So the attacker in this case can actually request for and get a bunch of keys corresponding to different identities. And this turns out to be the main challenge in the security proof. Okay? So then the attacker declares M0, M1. So this should be shifted a little bit here. Or it doesn't really matter. So the attacker gives M0, M1, and then the challenger picks a random bit, gives the ciphertext corresponding to the bit. The attacker could make more secret key queries, and then finally, it'll have to guess which bit the challenger picked, and it'll win if the probability with which its guess is correct is non-negligibly better than half, right? So this is a very natural game. The main new thing, as I said, with respect to something like FHE is that the attacker actually gets to ask these secret key queries. And as our primitives get more and more sophisticated, this turns out to be the main hurdle. So in particular, for the experts in the audience, or even for those of you who've heard all this buzz around indistinguishability obfuscation, right? Or functional encryption, I mean, handling this sort of partial decryption, this turns out to be the main hurdle. You can get semantic security, and we know how to compute on encrypted data, but the ability to get keys that give you something but don't give you the whole thing, this turns out to be delicate even to model, not here, but in general, and it turns out to be very difficult to achieve. Okay, so is this definition clear? So what I have to show you is how to achieve this definition, right? Question? Yeah.
There's this thing about like selective versus non-selective.
Yeah, that's what I was saying. So I'm just looking at selective, where the attacker outputs the ID star at the very first step. So this is of course bad. I mean, it doesn't model anything in reality.
Yeah, so you can't choose my name.
Sure. I mean, actually, is one of the questions I ask in my crypto class, like what's the real world motivation for selective security? The answer is there's none. It's just that, you do it when you don't know how to do the real thing, which is adaptive security. It's just a weakening to make things work. Yeah.
So does it mean this specific scheme we don't know how to prove adaptive security, or is
No. Good. No, IBE, we do know how to prove adaptive security. It's just that I will not do it.
No, but this specific scheme, the
CHKP? No, I think that's a good question. I think the original paper, are any of CHKP here? Okay, I think the original paper does selective security. I mean, P has been around, but yeah, he doesn't seem to be here right now. I could be wrong. I think the original paper does selective, but I'm not 100% sure. And then later this scheme was improved, which we'll see. And for that, we can definitely do adaptive. So whether the original scheme you can also do adaptive or not, I don't know off the top of my head, and I don't want to think about it at this moment. So yeah, so for now we'll just look at selective.
Shweta, I think it's important to know that if you are willing to pay a cost of in the security reduction, you get adaptive.
You mean the complexity leveraging argument? Yeah.
If it's in terms of cost, then you can generically go from selective to full. The two notions are equivalent.
Yeah. Yeah, absolutely.
That's right. That's also, I think, what he's pointing out.
No,
That
no,
you
no,
can.
that's with an exponential loss. I'm saying even without exponential loss, if you didn't care about efficiency, you can still do it.
How?
So there's a generic transformation from any selectively secure IB to fully secure IB.
Oh,
Well, this was recently that you guys had, right? Yeah, good, good, good. So that is something.
Yeah, not the same.
Yeah, so he's saying it's generic. Yeah, so this is the Garg.ling. Yeah, good, 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 very good. So yeah, so you can go from selective to adaptive. Okay, so anyway, for the purpose of my talk, I'm just going to do selective. So here are the key points of the security model. I've already discussed them a little bit. So it's funny because the last talk, I was done way early, and I can see that I'm following the opposite trend for this talk. But anyway, so we need to be able to answer the private key queries of the adversary, and the main thing, of course, is that the challenger needs to be able to leverage the hard problem, so cannot have the master trapdoor that you have in the real scheme, right? So in particular, there are queries that the challenger should not be able to answer, and that's very important. And of course, the challenger needs to embed the LWE instance into some kind of challenge ciphertext, so as to break the underlying hard problem. To achieve these simultaneously turns out to be a bit difficult.
By challenger here, you mean the reduction?
Yeah. So challenger according to this picture. So she gets this hard problem, and then in the end she gives a solution. So here's the simulation. So this is, now you'll see why we wanted selective security. Okay, so the attacker is going to give me some ID star. Let's say it's 1, 1. So now I cannot have the secret key for ID star. I cannot have the basis for A0. So what am I going to do? Well, again, given the scheme that I showed you, it's kind of natural. So anyway, for A0, I cannot have a trapdoor. Now what I'm going to do is that the A matrices that correspond to the ID star, I'll pick those to be without a trapdoor, and their complements I'll pick to be with a trapdoor. So now it's immediate that any identity that is not equal to that particular ID star, the F matrix corresponding to that is going to have at least one green matrix in it, right? Just the way that I picked it. And then using, this trapdoor extension mechanism, it means I can give you a key corresponding to this matrix. So I can answer, key queries for all identities except ID star. But I, of course, cannot answer it for F11. And in particular, this is how I'll get my challenge ciphertext now, right? So my challenge ciphertext is what? So ignoring the U thing, it's basically F times S plus E, right? Ignoring the U and ignoring the message. So it's interesting that in most of these encryption schemes, the message is the least important thing, right? So what you want is just Fs plus E. But since these are all red, I can get them from the LWE challenge. So these are all the LWE matrices, and either this times S plus E or random, I get from the LWE challenge, and this is now my challenge ciphertext. Any questions?
How do you embed the lattice problem there?
What?
Like you have the LWE instance?
Yeah.
Embedding?
That's what I was just talking about. So what you do is the following. So you're just going to receive, so F11, which is a matrix here, right? And F11 transpose S plus noise or random. This is something that your LWE oracle is going to give you. You see? So this F11 is anyway part of the public key. But this LWE sample here is going to be used to generate the challenge ciphertext. So if you go back and see the ciphertext, right, it's basically this. So this is something which the LWE Oracle gives me and I just drop it in. And similarly for the U. So you can think of it as like this F11 concatenated with U, it's one big matrix. The LWE Challenger or LWE Oracle gives me that matrix along with the corresponding LWE sample, which is matrix times S plus E or random, I don't know which. Whichever it is, I'm just going to construct my challenge ciphertext with it. Now notice that if it's random, then it hides the message, information theoretically. So now if the attacker can distinguish between M0 and M1, then it must have been LWE, right? Good. Any more questions? Okay, great. So we've made progress. So we have, one IBE that we saw, and we also saw a proof. Now let's see if we can improve this IBE. Okay, so one of the main disadvantages of the previous scheme was that this matrix was really big. So, you had to, and I mean the matrix is important, right? So this F matrix, it's what dictates the size of your public key as well as your ciphertext, your secret key, everything. So everything grows proportional to the length of the identity. So let's say we can improve that. So now what I'm going to do is instead, so the A0 stays the same, the U stays the same, and this A0 and U as well as their corresponding ciphertext counterparts, right? This A0S plus E, US plus E plus message, these are going to be invariants in all the schemes we see. So these will always be there. The difference will always be what else you do here in the middle. So now what we're going to do is we're going to make use of our favorite matrix G. And now we'll see, how to connect it with the trapdoor constructions that we saw. So now I'm just going to have A1, just one matrix, okay, and I'm going to have this public matrix G. This need not even be sort of explicitly stated. This matrix is known to everybody, so you don't even have to sample it or anything. The length is independent of the length of the ID. MSK stays the same. Keygen also stays, as I said, almost the same in the sense that there's an FID and you want to sample this E so that this relation holds. The FID is different. So this is our FID now. So A0 is as before, but now instead of this concatenation, I'm going to compute A1 plus ID times G. So for now, let's just think of ID as a scalar. Or if you want, you can think of it as an invertible n by n matrix. Okay? So, I mean, it's great, right? Because I can actually, like if I think of it as n by n matrices, that's a big space. So I can hash any, previously it had to be binary, now it need not. So this is my FID. And the real scheme, the rest of it stays the same. So as before, I mean, I have a trapdoor for A0, so no problem computing a trapdoor for FID, right? So I get a key, no problem. Ciphertext is exactly the same as before with a fresh FID. Decryption is regev decryption exactly as before. Okay, so the scheme is exactly the same as regev encryption with this new FID. So the main thing, of course, so this slide is just showing that this, ciphertext will be now much shorter. So the main thing is the proof. Is the description of the scheme clear to everybody? Okay. It's like a wave of nods going around. All right, so I'm going to assume that it's clear. If it's not, please ask me a question. Let me show you the proof. So as usual, I'm going to think about the selective game in which I assume that I have the ID star. But now the proof is a lot more sort of involved. Again, of course, I don't have a basis for A0. I do have a basis for G. the sort of new thing that we do in this proof is that we set A1 differently. So since you saw, or if you saw the previous talk about trapdoors, this is exactly like that. It's exactly like that. I mean, I should say that this came before that. So A1 is set as A0R minus ID star G. So of course there you don't have this ID star, but the rest of the structure is the same. So also exactly as we saw in the previous talk, by the leftover hash lemma, I'm going to be able to argue that A1 is uniform. Yeah. So R is again, I mean, so in the original paper we just chose it to be binary. Think of it as a large square binary matrix. It could be different things, but you know, it just needs to satisfy smallness and the fact that it's big enough to make LHL work. So this is my A1. Okay, so this is my FID. I'm going to keep it over here. All right, so now this is how we constructed FID before in the scheme. If I, you know, rewrite it, sort of substituting the freshly chosen A1 here, then I get this, isn't it? So this is the matrix I end up with, A0, A0R plus something G. Now one thing to note immediately is that when ID is ID star, the G goes away, right? So your trapdoor dies, and this is a good sign, because for the challenge identity you should not have any advantage at all, right? So now what's left? Well, of course I need to argue to you that I should be able to find a basis for FID given a basis for G, but I spent the whole of the last talk arguing that, right? So this is what I showed you in the last talk. So this was like my takeaway for applications. Like if you didn't follow anything in the talk, at least just remember this, that if I construct a matrix in this way, right, then I'm able to invert LWE and SIS on this matrix. So this of course was for MP12. I should mention that we did this already in ABB 10. So the trapdoors were constructed after you know, these techniques were used in the IBE, but it's cleaner now to think of it sort of it's cleaner to think of it as the trapdoor first in hindsight. So yeah, as I already mentioned, when ID is ID star, you know, this trapdoor vanishes, and I want to actually write down what FID looks like when ID is ID star, right? So when ID is equal to ID star, then FID becomes just A0 and A0R, right? Can everyone see this? And what does my challenge ciphertext look like? So my ciphertext looks like FID transpose S plus noise, right? Again, I'm going to ignore this U transpose S and A0, well, A0 is inside this. I'll ignore the U transpose S, because that we already saw we can build it from LWE. The new thing is the new FID, right? So let's focus on that. So this is my FID, and my challenge ciphertext I'll write here so everyone can see. My challenge ciphertext essentially looks like this, right? So what is this? This is basically so this is noise. So this is what I want to be able to construct. So now how will I do this from LWE? Well, I'm going to just receive A0 transpose S plus noise, okay? I'll pick the R myself and I'll just compute. So this A0 transpose S plus noise, this I have, right? But now I need R transpose A0 transpose S plus some other noise as well. And how can I construct this? Well, just from this, right? So I have this, I pick the small r and I multiply it to the sample. the error distribution, goes wrong a bit, but there are multiple different ways of fixing that. The way that is simplest to think about that Damien hates is just flood it. I don't think he'll ever ask me to give a talk again, but it's maybe the simplest way to think about it. There are many different things you can perturb it. Maybe that's better. Everybody is happy. Okay, so you can fix the noise distribution. This is how you create this. So is it clear to everyone that for ID equals ID star, I can embed the LWE sample into a challenge ciphertext? That's clear? So then what we need to do now is just answer key queries. And this, as I told you, follows from our trapdoor stuff, right? So to summarize, this is, the real system versus the simulation. In the real system, you have a trapdoor for A0. In the simulation, you have a trapdoor for G. A1 there is, random. Here it's picked in this special way, which by the leftover hash lemma says that it looks the same as the real system. The encryption matrix is exactly the same. When you write down the new A1, it looks like this. What this means is that whenever ID is not equal to ID star, you can get a short vector. Here you can always get a short vector in the real system, right? So that's the main difference.
Shweta, isn't the MSK and the simulation R together with the trapdoor for G, and mostly R, right?
So I guess it's a aesthetic question, like what do you want to call the trapdoor? So R is something you sample, you sample yourself. You could think of it as R. So yeah, I mean the short answer is, of course you use the R, you also use the trapdoor for G. The R is something which you sample yourself. You could think of it as the main trapdoor.
But I'm saying it's a trapdoor for G is public. G is public and the trapdoor for G.
Yeah, that's true. That's true. Yeah, that's true. So yeah, I guess that, I maybe want to mention this thing here, that this gadget matrix G is actually not sacred to this scheme. So in fact, the original scheme was developed using any arbitrary matrix. We called it B, B versus G, but the point was that it didn't have to have the special algebraic structure. That's the point. This, by the way, is not true when we go to more advanced things like attribute based encryption. So there, the G is more important because you need to have a public trapdoor there. But in the IBE, you don't need this trapdoor to be public. So you could, if you wanted to, replace this G with, another matrix, B, sample its trapdoor in the simulation, and then that leads to a trapdoor, it leads to the R and so on and so forth. Okay, so, but yeah, we know this, right? If we do stick to G, then it makes more sense to think of R as the trapdoor rather than G. Good, thanks for pointing that out. Good, so now let's move forward. So I want to show you inner products and then circuits, okay? So we have point functions. So we are able to compare, 2 points, one in the ciphertext, one in the key. What we want to do next is have a vector each. One vector in the ciphertext, one vector in the key. And I want to be able to decrypt if the inner product is 0 and not otherwise. So notice that this is different from outputting the inner product, which are also schemes that you can construct. But that's not what we're trying to do here. I will not, say anything about this. It captures a few things, but as far as I'm concerned, it's about expanding the function class. So now, the nice thing is that you can bring in some arithmetic operations, right? So in particular, it's sort of nice that now you can do one multiplication, one addition, you can do these inner products. And as I already told you, going ahead, I want to be able to do arbitrary computations. Okay, so let's see first how to do inner product. So now I'm setting the length of my vectors as 4, and it's a bit bad because I need sort of 1 matrix per position, but I don't need 2 per position, but this is what we need. Okay, and A and U is as before, so you always have that. MSK is exactly the same. It's always about this F matrix and how you define it. So now what I'm going to do is, if Y is the vector in my key, so X is in the ciphertext, Y is in the key, I'm going to define Fy as A concatenated to summation Yi Ai. Okay, this is my Fy, and I'll give you a key corresponding to that. Is it clear to everyone? So now remember that we've moved past IBE. So the F matrix is now actually going to be different, right? For the key and the ciphertext, it's not the same string in the two things. One has a vector X, one has a vector Y. So each one has to give you some information corresponding to its own X or Y, but we have to be able to evaluate on it and end up with a matching key and matrix. So what's going to happen is the key generator has computed this Fy. Okay. Now the encryptor will not give me a regev encryption for this matrix. That's obvious, because well, it doesn't even know Y, and right, it wants to do inner product. So now what's going to happen is the encryptor will give me some other thing, but the linearity of the system or the linearity of the ciphertext will allow me to collapse that into exactly this Fy if and only if X inner product Y is 0. Okay, so the key generator encodes the function, okay, in this matrix. The encryptor does not know the function, it's going to give you something else. Let me show you what it gives you. This is the main new thing. So these are our fixtures from before. This is the main new thing. So it's AI plus XIG transpose S plus noise. Okay, this is our ciphertext. So you're encoding this vector X in the ciphertext in this way. And as we're going to see in another 5 minutes, encoding it in this way is actually beautiful. I mean, it's going to let us do not just addition, which is very natural, but it will also let us do multiplication, as we'll see. So this is our CI. Okay, so yeah, the ciphertext hides Xi, but let's even forget about that. So the main new thing in this scheme is how to compute on this ciphertext. So I want to ultimately evaluate X inner product Y, right? Is everyone with me? I want to evaluate X inner product Y. I have these encodings of each bit of X. So what's the natural thing for me to do now to compute X inner product Y? Any ideas? I have the CIs, I have the Y with me, and I want to compute X inner product Y in the ciphertext. How should I do it?
Why?
I'm looking at my students.
Why I see it?
Did I show you this in class already? Okay. Very good. So yeah, so what will you do? Well, you'll compute summation YICI. Again, it's very natural. I mean, given this ciphertext and given the functionality, what else are you possibly going to do? You'll notice that the Yi had better be small, otherwise the noise will kill you. Let's ignore that. So you can again fix this with the bit decomposition that Vinod talked about. So I'm going to compute summation YICI. It's going to look like this. Now what's the neat thing? Well, if X inner product Y is 0, then this goes away. And then when I concatenate these two, I get this LWE sample whose label or whose matrix exactly matches the one for which the key generator gave me the key. Okay, so it's a very nice algebraic structure that we follow here. Let me generalize it even a little bit more. the key generator has some function and encodes it somehow into some matrix, right? So here let's think of this as some A sub y. So again, how he encodes it is not very important, you know, for an abstract framework. Somehow you encode the function, which here is a vector y, into this matrix. The encryptor gives you these encodings of x in a way that are somehow amenable to computing f of x encrypted. So you know, it's like FHE. It's actually exactly like FHE, right? You have ciphertext. You're computing some function on the message. Here you can think of the message as being the x. So the encoding is a bit different and so on, but you know, actually for GSW, FHE, it's not even different. But anyway, coming back to, you know, the current theme, you have these CI, they encode x, you compute f somehow, right? In this case, it's easy because you just do summation yi ci. And then if you compute f of x within the ciphertext, whenever it is 0, the g part goes away. So the x goes away, the g goes away, and what are you left with? Just something that encodes f. So this, you know, think of it as like a functional ciphertext that encodes f in the end. If f of x is 0, then x dies, right? And all that remains is f. But f was something that the key generator always knew and gave me a key for. Okay, so decryption will work. So you just do regev decryption. Questions? So this framework is really very general and it's very, very sort of pliable. You know, like you have these, it's really a lot like FHE, but you have to sort of, the key difference from FHE is that when you evaluate on these ciphertexts, you have to make sure that whatever, you know, resultant ciphertext you get is something that is amenable to regev decryption using information about the function f. In FHE, if I evaluate on two ciphertexts and I stare at it and try to write it as an LWE sample, the label, you know, there is no good control we have on the label or the matrix of that LWE sample. It could depend on x. But here you need that after the evaluation, the label here that you get, I guess, I don't know if this is clear or not. You know, please tell me if not. What I'm sort of trying to say in many different ways is just that I've got these ciphertexts. It's like FHE. I evaluate on them. The point is that when f of x is 0, I should end up with an LWE sample whose label depends only on the public key and the function. You see that? Because only then is it possible for the key generator to have given me a matching key. Right? So the key generator, sorry, so you know, till more people nod, I'm not going to stop. Okay, so here's another way of seeing it. The key generator has a matrix in her head. Okay, it's A sub y. It encodes the function. I don't care how it encodes the function. The encryptor knows nothing about y. It has its x. It encodes its x. It gives me these nice encodings which are very, very amenable to computation. I compute on them. I end up with an LWE sample. Okay? The LWE sample has a matrix. This matrix needs to be the same matrix that the key generator had in her head. If these two match up, you can decrypt. And all of this stuff, IBE, ABE, FE, all of this, is, at least when it's based on LWE, is really this is what it's trying to achieve. The key generator and encryptor do not talk. If you're the key generator, you have a function, you came up with a matrix. I'm the encryptor, I don't have a function, I have some input, but when I compute on that input, encrypted, I better end up with an LWE sample whose matrix is the same matrix that you thought of, and then it will work. Okay? So is it clear? So now people just want me to stop talking, so everyone's nodding. All right, that works too. So let's generalize to circuits. Okay, good. So here's this is really cool stuff. So this was our ciphertext structure from before. And previously we could evaluate on the ciphertext to obtain this, right? Ay plus f of x, which in this case is x inner product y, g, an LWE sample with that. The question that we're asking is, can we generalize this to arbitrary functions? So notice that y is public, right? So you noticed that during decryption, the decryptor knew y and therefore could compute summation yi/ci, right? So what we did was linear. It wasn't really quadratic, right? It was known scalars. So it was sort of scalar multiplication and addition, not yet full multiplication. So of course full multiplication now, that's the big question, right? So you want to be able to do xi xj, not just yi xi, but xi xj. That's what you want. And to sort of state it a little more clearly, I want to end up now with this guy. So this is my sample that I want. Okay, so I'm going to be given the same CIs, and I want to end up with A sub f. So notice again, this A sub f is something that the key generator can figure out for herself, plus f of x g s plus noise. Yeah. So the matrices have to match up. When f of x is 0, this will go away, and again I'll get what I want. Good. So how to do it? So this is a really beautiful work by Bonnet et al. And I'm going to just show you one multiplication for concreteness. Okay, so I have my C1 and C2, they encode x1 and x2. And I want to end up with A12. So I want to end up with some A12 plus x1, x2g. I want to end up with something like that. So A12 should depend only on the public key and the function f, right? The function f here is just 1 times 2, I mean whatever, x1 times x2. So I want to end up with this, and the question is, can I? So I found this result really beautiful. Yeah, this is just writing what I wrote there. Because it makes use of this really neat observation that we're not trying to hide x. So somehow, I mean, when I first, if I first think of this problem that I want to do x1, x2 inside the ciphertext, it doesn't, to me, it doesn't sort of immediately, it's not immediately obvious to me that you can use x. Like you think of it as FHE, that you don't know x and you want to somehow end up with this. But the cool thing here, and what makes this application possible, is that you can use x. So how do you do it? This is how you do it. So first we just do some simple algebra. So let me just take these matrices. Okay, so I'm going to forget about S plus noise. I'm just writing down the matrices. Yeah. So we take the first matrix and we multiply, well, we'll multiply G inverse of minus A2 to this matrix. Okay, and to the second matrix, we'll just multiply x1. Okay, so what do we get? Well, here we get A1 G inverse minus A2 minus x1 A2. So the G goes away, right? So this G inverse is nothing but the SIS trapdoor inversion. So what is this G inverse minus A2? It's some sort of square matrix such that G times that matrix is equal to minus A2. We've seen so much of this by now, right? So this G and G will die. So I'm going to get minus x1 A2. And now you can immediately see that that's what I'll also get here, and we'll cancel it, right? So this is just going to give me x1 A2 plus x1 x2 G. So you see I got x1 x2 times G, And when I add these terms go away and I get A12 plus X1 X2G, which is what I want. But of course, this I did only with the matrices. I have to do it with the LWE samples. But why does it work? Because these transformations I applied are small. So it doesn't matter. I mean, between the matrix and the LWE sample, the only issue is the noise. But as long as my transformations are low norm, you can contain the noise growth and it's not going to matter. Okay, so just to make it explicit, here's my C1 and C2. Let's say that R is G inverse of minus A2. So I'm going to compute C of X1, X2 as R transpose C1 plus X1 times C2. This is what I did in the previous slide, but now instead of the matrices, I'm applying it to the ciphertext. Yeah, so I got the sample that I wanted, right? As I already said, it makes use of the fact that R and X are small. And then my A12 looks like that. I don't actually care what the A12 looks like too much, as long as it's a function dependent thing and doesn't depend on the inputs, right? For those of you who've seen the GSW FHE scheme, this is exactly how you evaluate on the GSW ciphertext. So it's really very, very connected. So yeah, I already said this. So since these are small, they don't affect the noise. And then of course you have your usual things. And this is going to let you do regF decryption. So in particular, I concatenate C X1 X2 to C prime. And this gives me A12 transpose S plus noise, right? When X1 X2 is equal to 0, then this becomes exactly this, right? The G term goes away. And this is exactly what I have the key for. So to derive the key as usual, I'll use a trapdoor for A. I'll compute A12 on my own. I'll extend the trapdoor. I'll sample the E to satisfy this, and I'll hand it out as the key. So I just perform regF decryption. So I mean, for concreteness, I've written it down here. You can check. But yeah, it's just regF decryption. Any questions?
Technically, you previously said that in these instructions you cannot replace a gadget matrix with a...
I didn't actually. I remember I said that for IBE you can replace the gadget, but in this you need the trapdoor.
Yeah, but I was thinking you can actually, right?
I mean, you could have like a B and B inverse, which is public, I guess. But the point is you need the trapdoor.
Yeah. The only place where this is needed is for bounding the error, right?
I mean, you need the trapdoor to sample these things, right? Like this G inverse A2 and so on.
I thought in these constructions, the image, when you compute the bit decomposition with respect to G inverse, then the norm of those vectors is appropriately bounded.
Yeah.
Very, very small.
Yeah.
But if you take any random matrix,
Yeah.
then the norm of that
Yeah.
that small. And that's
Yeah, but I'm saying, sure. I mean, you could use, something else. I guess what I was saying was, or what I was trying to emphasize was that you do need a trapdoor. You need the evaluator to have a trapdoor. So in the case of G is public. The evaluator has the trapdoor. What does this mean? It can compute G inverse of anything that it wants. And this is actually needed in the ciphertext evaluation, right? Because if you remember here, so this ciphertext evaluation over here needs this. And it's pretty imperative. I mean, there's no way to get around that. So in order to sample these guys, you need to have the trapdoor. That's all. Yeah, I don't think that there's anything other than the parameters. I don't think there's anything very sacred about the G. But just that, like in the IBE, you don't even need the trapdoor publicly. But in the ABE, you do. So in that sense, it makes more sense. Good question. Other questions? Okay, so I'm hopefully getting close to being done. So regif decryption and then everything works as before. Okay, so more generally, this is like a very neat sort of, you know, two-line summary of what we did. It's the following. There exist small, so this small is not terribly small, we will talk about that. There exist these small matrices H hat and H, where H hat depends both on F and on X and H depends only on F, such that if I take you know, the concatenation of these matrices and I apply H hat to it, then what I get is this A sub F. So the A sub F can be written as a sequence of A's times the low norm transformation minus F of xg. Okay, so this is a very sort of concise way to capture, you know, what we were doing. We did it for one multiplication gate. This shows you that it can be done for any F, right? So of course, it's natural that it can be done for any F, given that we did one addition, one multiplication and ended at the same invariant, right? We ended at the same ciphertext that we kind of started with. So it's natural that you can keep going, but this captures it very nicely. We call this A sub F, and I just want to point out that the left hand side sort of implies that this H hat is the transformation that you are applying to the ciphertexts. Okay? So that's why, because it's small, the noise is not growing too badly. And yeah, of course, the key generator provides the matching key. So this, I guess I've said many times by now. So it just encodes the function into a matrix and provides the key. So it's really cool what we get in the end, right? So the encryptor takes X and a message M, outputs a ciphertext. X here is public, M is not. The key generator takes a master secret key and a function F. This function now can be any polynomial size circuit. It outputs a secret key. Decryptor takes the secret key and the ciphertext, returns M if and only if F of X is 1. This works for all circuits, which I think is really neat. Of course, you have a setup. This is attribute based encryption. Okay. How much more time should I take? I know I'm out.
5 to 10 minutes.
Okay, 5, even 5 is fine. So I just want to, I mean, this is my last maybe 2-3 slides. I just want to say a little bit about the proof. So we spent a lot of time looking at the IBE proof, and it turns out actually that the same broad structure is going to work using trapdoors that we constructed. So I do want to say something about it. So first we'll just go over the definition. It's just like IBE, right? So you have this key request phase where the attacker can request for keys of her choice. And then, you know, she submits 2 messages M0, M1 such that none of the functions, sorry, this should have been here actually. Yeah. So none of these functions applied to the challenge attribute should give 1. So this condition, is really, it's just so that the security definition is non-trivial. So why? Because the adversary submitted some challenge attribute X star, okay. Now if I am the adversary, I gave you X star, and then suppose I ask you for a key so that F of X star is 1. Okay, so if my function satisfies the attribute, then I should be able to decrypt. Actually, I guess that in the constructions I used 0 as the decrypting condition. So this should be 1 here. Okay, so it's just a matter of notation. Okay, but it's important obviously. So if I am the attacker, I gave you some X star and then I requested some key so that F of X star allows me to decrypt. whether 0 or 1. Then obviously later when you give me a ciphertext corresponding to X star with either M0 or M1, then my key will legitimately let me decrypt and disambiguate, so that wouldn't make sense. So just to, you know, sort of not have that problem, we'll have this condition. Okay, so forget 0 or 1. It should be that Fi of X star does not let me decrypt a ciphertext corresponding to X star, okay, whether 0 or 1. The rest of it is exactly the same. So these are also exactly the same. I just want to mention that these private key queries will now be much more complex to handle. The rest of it sort of is similar. So I just want to say, as I said, a few words about the simulator strategy. Okay, so first let's see how to make the challenge ciphertext. So this actually looks almost the same. Okay, so I set AI in this way as we did in the previous construction, and you know this is going to become ARI transpose S plus noise when X is equal to X star, right? And this can be simulated exactly as we saw before. So the challenge ciphertext is sort of as before. Basically this you know, Xi star G thing goes away, and I just have R times AS plus noise. Okay, so this is not anything different. The key queries, well, they're also, handling them is similar to before, but you have to use more powerful machinery. So what we can show is that, you know, when you set AI in this way, and then you compute A sub f, the key generator, remember, computes A sub f, that actually looks like this. Okay, so just trust me on this, or look at the paper. This is what you get. And the key, of course, was this, right? So what you need to be able to answer a key query is a trapdoor for this matrix as long as the decryption condition is not satisfied. But this follows from the trapdoor construction I showed you. Okay, so in particular, this is what we had. So if you have AR minus HG, then the trapdoor construction tells you that given R and G, I can get a trapdoor for this whole thing. And now I just want to point out that this matrix for which I need a trapdoor in order to answer my key queries, it looks like this. So it's A concatenated with A sub f, where A sub f is A R sub f minus Fx star G. And Fx star G here is non-zero, right? So it looks exactly like this, right? So it looks like, so this R will become Rf and this H will become Fx star, but it's exactly the same thing. So this shows me that when f of x star is not 0, I can answer key queries. And when f of x star is 0, then this trapdoor goes away. And in that case, I don't have any way to answer key queries, which is what I want. So that's all. I just want to, so this was clear? So it's really the proof sort of follows from these trapdoors, and the fact that, you know, this evaluation gives you this nice structure here. So the algebraic structure of these objects, you know, fits very nicely with the trapdoor construction. So the fact that this A sub f looks like this is what lets you invoke this and answer queries. It's very neat. Any questions? Okay, so there's actually a lot of open problems in this area. The first one, which is a favorite of mine, is ciphertext policy ABE. We know very little about this. From LWE, we have almost nothing. So this is the problem where you put the function in the ciphertext and the x in the key. So what I showed you was the x was in the ciphertext and the f was in the key, right? Now I want to swap them. And actually, if you think about my motivating example right at the beginning of the last talk, maybe you don't remember, but We had this example of someone who wanted to encrypt a file against an access control policy, right? That makes more sense to me than, it makes more sense to have the access control policy with the file rather than with the person.
Can't you have like a universal circuit?
Of course you can have a universal circuit. We don't want a universal circuit, we don't like them. It's not efficient, it's not even elegant. So that's a no, like many people will be angry, but
But why not?
What?
Forget efficiency.
no, come on, Vinod.
No, wait. In principle, what? Like,
I guess
Then I'm on the side of the efficient, guys. It's inefficient. I think it's inelegant.
I guess the size of the circuit has to be bounded, right? In setup time, that's the only constraint.
No, that's not the only constraint. I think it's interesting to ask for CPAB even when the circuit is bounded, but then you don't want both key and ciphertext to degrade with the size of the circuit. I should confess that these are at this point, well, all of these are really feasibility results. I mean, they are very far from being efficient at the moment, right? So maybe this universal circuit transformation, okay, it adds one more Pauli factor, but to be more serious, the reason I don't like that solution is because I feel like it avoids the problem. I mean, we need to have new ways of handling, this circuit embedding. So this is my take on it. You can do universal circuits, but it's either inelegant or inefficient or some combination. In any case, I don't like it. It also doesn't let you, the universal circuit doesn't let you support unbounded size circuits. So if you want like a mathematical, primitive that kills the universal circuit option, then that's you can ask for the circuit. Just that there's no bound on the circuit size. So you can't do universal circuit.
Even the key policy one, you can't do that right now because the depth dependence is there. So
Depth is one thing.
that is not there in either, right? So
Okay, let me think about it.
yeah.
Okay, so good. So depth dependence is actually my second open problem. So maybe I can just reorder the problems. But it's true that you have depth dependence, but you don't have size dependence. If you want to do universal circuit, there'll actually be size dependence, which is much worse. Right? Is that makes sense? So because in the universal circuit, the function is also an input to the circuit. So there's a universal circuit is some circuit U, which takes as input some function f, some input x, and then gives you f of x. So if I want to convert a key policy ABE to a ciphertext policy ABE, then I'll have to sort of take my function as a long string. And this means that it, the ciphertext will grow with the size, everything will grow with the size of the function, not just the depth. So it's much worse than the key policy setting.
Okay, so in the key policy ABE, when I encrypt an X, I don't need to know how big a function, modulo the depth issue.
Yeah, but he was pointing out, yeah, that's exactly what I said.
Modulo the depth issue, I don't
Yeah.
need to know how large a function is going to be.
Yeah.
Whereas if you do the universal circuit
Yeah.
thing,
That's exactly what I said. Yeah, that's exactly what, you're exactly right. Yeah. The second reason or the second open problem is that the parameters of these constructions are really bad. So in particular, the noise growth is actually exponential in the depth. So this is really sort of bad, and I think that it's really a sort of very important technical barrier in my opinion, which I have and I'm sure others have, tried to get around, but it's really a problem at the moment. Okay, and it forces you to have sub-exponential modulus to noise ratio and so on. So improving parameters is important. one line of work that I like is to replace circuits with, uniform models of computation, DFA, NFA, Turing machines, random access machines, and so on. From LWE, actually very little is known. So there's some partial progress that we had at crypto last year, but this is restricted only to the secret key setting. And it's really, I think, important to come up with new techniques to handle the public key setting. Also, we cannot handle Turing machines. So we can only handle NFAs and a little more, but Turing machines is open. Adaptive security is a big problem. So again, I think it's a favorite problem with all the people who have worked on this topic. So in the pairing based constructions, you have some techniques, but we don't know how to make them work for LWE. I think that, so when we read the description of this workshop, it says that bring together people and look at like the important problems. So I would say that 1, 2, 4, this is maybe more of a personal favorite, but like this and this are sort of really central questions in this space. Adaptive security, broadcast encryption from LWE. So here we have a solution with Shota that uses pairings in LWE and gives you broadcast encryption with optimal parameters. But obviously you want to get it purely from LWE. I have Vinod's permission to mention, I still have it. I have Vinod's permission to mention that he and Zvika have a scheme, a very cool scheme which I have seen, which also does broadcast encryption, does not use pairings, it uses LWE, but it's not provably secure based on LWE. So, its security is kind of hard to understand, but maybe he'll give us a talk about it. It's pretty nice. So yeah, this is a small selection of some of the problems I like. There are many more. If you're interested, come talk to me. Thank you.
Good time for one quick question.
Yeah, maybe I have one.
Yeah.
Even for IB, we don't have adaptive security?
We do. For IBE we do. Good. Thanks for asking that. So I meant for ABE. Yeah. Yeah.
Not super efficient.
I mean, nothing is efficient.
What was that question?
No, he asked whether we have adaptive security. Do we not have it even for IBE? So for IBE we do have it using the CPRF thing, but we don't know how to do that for ABE. We have a tight reduction actually for IBE. Other questions? So really there are lots of open questions here. If you're interested in this topic, please feel free to talk to me. I feel, and I know that this feeling is shared by many of us in this room who work in this area, that the real thing we are lacking is more techniques. And it's really a very frustrating place to be, because I feel like even the new results, we see many of them, they're about bypassing they find clever ways to bypass the issues that we don't yet know how to handle. But these issues that we don't know how to handle have been there for years. Vinod, would you agree with that? Okay, this is what I think. So, yeah. Okay, good, thanks. No, because you looked, so I wasn't sure if I should, rephrase something. But for instance, this depth dependence issue, the fact that the noise grows exponentially in the depth, okay? I want to not offer money for the problem. I was on the verge. No, I do not offer $100 for this problem, but...
That's Chris's, Chris Piker's.
Come on, that's an insult, man. Who's going to solve a problem for $15?
I didn't say it. You said it.
Oh shit, and I'm on video, I'm dead. But, okay, I offer you, 500 mental dollars. Like I mean, it's purely $500 of appreciation. If you will solve this problem, you know, really we need a solution to this problem. It's actually related to this problem. So, you know, if you try to build anything for Turing machines, actually this depth dependence kills you, because a Turing machine has unbounded input length and unbounded poly running time. So this depth dependence will not even let you instantiate a queue. Yeah. So there, like I said, it's really an important problem. And broadcast encryption and CPABE are equally important. So yeah, 500 mental dollars for each of them. All right, I'll stop here. Thank you.